In this question, we're sort of being asked to analyze the difference between acid-catalyzed and base-mediated ester hydrolysis. So from purely a theoretical standpoint, if we want to think about what we're trying to accomplish here, we have our ester, and you can think about it needing to essentially be reacted with hydroxide, which would be in equilibrium with carboxylic acid and methoxide. So thinking about this equilibrium here, well, you really don't have anything to drive this to one side or the other, because your stabilities on this side, on the left of the reaction, are pretty much equivalent to the stabilities on the right side of the reaction. OH minus and O-methoxy minus have similar stability, as does the ester and the carboxylic acid. So whether we look at this through acidic conditions or basic conditions, we're going to need to find a way to drive this reaction to our carboxylic acid product. And that's one thing we'll focus a lot on here. One other thing just to sort of take note, and this is an important feature, is that under the acidic conditions we're going to get to the carboxylic acid, but we only need a catalytic amount. Whereas under the basic conditions, we'll use hydroxide as our base, we need a full equivalent. Alright, so we'll look at each of these processes separately, sort of see the differences. Let's first take a look at the acid-catalyzed conditions. Okay, so the important part here is that we have an H+ source. Okay, in this case it's sulfuric acid. It doesn't necessarily have to be that, but that's what we're going to work with. So let's look at this through the reaction mechanism. Anytime we have a carbonyl like this in the presence of acid, what we're going to do is first protonate the carbonyl. So we'll use these lone pairs on the carbonyl oxygen to grab our proton. Okay, so this is important because now we have what we would call here an activated carbonyl. Okay, and it's an even better electrophile than a normal carbonyl. And that's good because really water is a pretty weak nucleophile. So it works good together to have an activated carbonyl to use with our weak nucleophile. So now we'll use these lone pairs on the water to attack our activated carbonyl. This oxygen has a positive charge. It's electron deficient, so we can push these electrons from the pi bond up onto the oxygen. So that becomes just an OH group, and now we have water attached to that carbon. Okay, we have 3 bonds on that oxygen, so we're going to give it a positive charge. Now at this point, you can think about this proton getting transferred to any of these species with a lone pair. We could transfer it to this ether oxygen, we could transfer it to this other alcohol. And in fact, both of those things are happening in this equilibrium. But we're just going to do the proton transfer step that gets us to what we want. And we need to eventually lose this ether group to get us to the carboxylic acid. In order to do that, we'll want to make this into a good leaving group by protonating it. So we'll just show the proton transfer step that involves transferring the proton to this oxygen. So now we have the proton on that oxygen, so we'll give it the positive charge. Now it's perfectly fine if you want to do a two-step process where you first remove this proton with base, and then a weak base like water, and then you can transfer the H plus to this ether oxygen. But I'm just sort of showing it as sort of a shortcut with the proton transfer step. Now we have this as our good leaving group. Okay, so what I'm going to do is I'm going to use lone pairs on this alcohol sort of to assist me in losing this particular leaving group. Okay, when we do that, we form 3 bonds to this oxygen, so it gets a positive charge, and then we just lose methanol. Okay, so now we can just use a weak base that's in solution. I'll just use water. And we can take that proton back off of the carbonyl. So what we've done here, now at the final step of the reaction, we have regenerated our acid catalyst. So this entire process is an equilibrium process. Okay, and the truth is, this leaving group of methanol that we used really is no better than water at this step. But that would drive, losing water would drive the equilibrium in reverse. So for this hydrolysis process, we really need to do something to drive the reaction to the right to get this carboxylic acid. So probably the most common way you would want to do this, since we're adding water in this first step, by using an excess of water, which is definitely your cheap reagent, that's an easy way to drive this reaction. Okay, another way you could potentially drive this reaction, since in this step you're losing methanol, you could potentially then remove this methanol as the reaction progresses, which will drive the reaction to the right, but also by taking away this methanol, you eliminate the possibility of the reverse reaction because it's not there to add back into this, driving the reaction to the left. So those are a couple of ways you can favor the carboxylic acid product under these acidic conditions. Now we're going to take a look at this reaction using the base-mediated conditions. So I have hydroxide through my sodium hydroxide, and this is a pretty good nucleophile. The difference here, now I don't have an acid to activate my carbonyl, so this carbonyl isn't as electrophilic as before, but because my OH- is a pretty good nucleophile, I can still easily attack that on my carbonyl carbon. So I'm going to attack that there, push those electrons up onto the more electronegative oxygen, which will give me an O-. So now I'm at this tetrahedral intermediate, and basically the OH and the methoxy group are equivalent leaving groups. So I can push that negative charge back down to reform my carbonyl. And I do have the possibility of losing my methoxy group, like that. Which gives me this carboxylic acid. But I have an equal likelihood that when that comes back down, I'll lose the OH-, just taking me back to starting material. So this is a complete equilibrium here, but under these basic conditions, we do have an extra driving force. And that's the fact that we generate this acidic carboxylic acid proton. Let me just show that attached. Okay, and the pK of that is about 5. So it's going to be favorable for me to deprotonate this to put the negative charge on this oxygen. So I can think about doing that. And this acid-base reaction is definitely going to favor going to the right. So I get O-, plus methanol. Now what I have here is a resonance stabilized anion. So this step really drives the reaction to the right. Since I use sodium hydroxide as my base, I can have Na+ sort of hanging around with this as its countercation to have this carboxylate salt. Just for comparison purposes, the methanol is much less acidic with a pKa of about 16. So that's why it's definitely favored to go to the right in this case. Now under these conditions, really what we've done here is a saponification process to form this carboxylate salt. And with these conditions, we're done here. Okay, this doesn't go any further. All of the product gets converted to this carboxylate salt, and you can't do anything else. But if you actually want the carboxylic acid, which is often the case in these hydrolysis reactions, what we can do is once this reaction is over, we can add some dilute acid. And that dilute acid will just protonate this carboxylate anion to give us the carboxylic acid. So to actually get to the carboxylic acid, it's a two-step process. First is base and water. Second is just a dilute acid. So we have a little bit different driving force under these conditions, but again we have a way to drive us to the carboxylic acid product. Another thing to take note here is this OH was used in the OH- was used in the reaction. It was never regenerated, so it's not a catalyst. It was used in a stoichiometric amount with our ester.